Hi, I'm Shrijan Swaminathan. I am an incoming third year at Purdue University, and I'm working with Fermilab as part of the DOE Omni Technology Alliance internship program. And I'm going to be talking about automated benchmarking for resource provisioning. That. All right. So before we talk about the automated portion, let's talk about why should we benchmark in the first place. So in high throughput computing, we use many resources, and the worker nodes on these resources are all very different from each other. And it's hard to gauge the difference between these different machines because of different architecture or different ratios between CPU cores and RAM. And to evaluate such a performance of them in such a way that is easily comparable, and you want to minimize as much error as possible when you're benchmarking. And you get better quality nodes can reduce costs on these clouds and optimize purchasing of cloud VMs, which transfers to higher throughput overall. So talk about manual benchmarking. When I was testing running benchmarks, I mainly used the PEPSpec 06 or HS06 benchmark to run tests on different cloud renting virtual machines, and I tested it with AWS EC2 and Google Cloud Compute as the basis. The main reason for running these benchmarks is to get the price to performance data of instances and to figure out what the most efficient instances to purchase based on hardware performance. So these are the instances I tested, and I defined the standard platform to have compatible benchmark results. This translated to 16 cores per instance and a variable amount of memory. In the Amazon portion, the C series indicates that's 2 gigs of RAM per core. The M series was 4 gigs of RAM per core, and the R series was 8 gigs of RAM per core. And the number convention that's listed there, like 3, 4, 5, that is newer architecture or older architecture. So increased number means higher architecture, and smaller number is lower, older. The I's and the A's indicate Intel and AMD. Same idea with Google's one, with the D indicating that it's AMD processors, and without anything, it was Intel processors. So these are some of the results that I got from these manual benchmarking. And the graph shown to the right shows the manual, so the raw hardware performance. And if you look at, there we go. So if you look at the C's to the M's, you can see a general trend of increase with the higher generation. And if you look at the M's right here, there's also still a general trend of an increase, and same with the R. And you can see that the higher the generation, the overall higher performance you generally get. And it's way more pronounced with the price to performance one, which I calculated with the on-demand prices at the time of running these benchmarks. And you can see that there's a much more significant increase between the 3 different, all the VMs. Yeah. So, well, since I tested on-demand prices, it's more consistent, but you can actually get it for much cheaper, and therefore the price to performance overall could be much more optimized with the use of spot pricing. And what the difference between on-demand and spot pricing is, you reserve a machine for on-demand, but with spot pricing, you bid for a machine essentially until someone offers more money or to buy that, to purchase that game. So yeah, again, so on-demand fixed pricing, spot varied pricing. And for on-demand, you can run for as long as you want, and it's a little bit more expensive in comparison to spot. In terms of well, in comparison to spot, yes, works and it works very similar to a service purchase. While spot has varied pricing, has the possibility of being preempted, but it can be much cheaper than on demand and works similar to like an auction. So using spot pricing can reduce the cost and overall reduce price performance as well. So use case of this, it's being used in HyperCloud's decision engine at Fermilab, which uses a spot pricing algorithm to provision the cloud resources. And it uses the values from the benchmarks to calculate the figure of merit for the VM types and minimizes the cost. Okay. So there are many different new platforms that are added all the time for benchmarks. And tailored benchmarks could optimize for different types of user jobs. So therefore, we need many different benchmarks, right? And when you're running these benchmarks, it's very labor intensive to an extent, right? And therefore, we need automation, hence automated benchmarking. So I was thinking about doing automated benchmarking via GildeinWMS. So it's what GildeinWMS is a workload management system that uses HT Condor to send GildeinWMS and provision resources. And GildeinWMS are pretty much pilot jobs in this scenario. And it has three main components: the factory producing GildeinWMS, front end, and the front end, which calculates the number of GildeinWMS required to finish the user request. And we would want to leverage the GildeinWMS to run. So difference between manual versus the GildeinWMS automated benchmarking that is proposed. Manual is labor intensive, as I mentioned earlier. You can run it on as root. It can run on bare bone hardware. And it's easier to customize because you're doing it personally. And there's limited resources for the benchmark, and it's being done in a controlled environment. While with automated benchmarking, it's much easier to run multiple at a time. And you have to run unprivileged because GildeinWMS don't have root permissions. And you can run within a container, and it's much more standardized and can be much easier to scale. So again, we're using containers, right? So containers provide a much more standard environment, and Apptainer, aka Singularity, which is unprivileged container runtime environment. And we would be using CVMFS to provide multiple rootless benchmarks in expanded images. And what this over here says is it's pretty much running the one of the Atlas Gen benchmarks that's in CVMFS as a Gleiden. And so proposed idea, GildeinBenchmark. It's a web application dashboard to automate benchmarks via GildeinWMS. And there's two main components: the runner, which triggers and monitors the benchmark execution, and the viewer, which serves and displays the results. And it should work with existing GildeinWMS deployments. And if you see here on the green, these are the GildeinBenchmark viewer and runners, which are connected to factory configuration and REST APIs here. And this is in the gray, that's where all the worker nodes are. And we're pulling the benchmark from CVMFS. In blue, it's factory and GildeinWMS themselves. So runner. runner executes on the desired resources selected by the user by controlling the GildeinWMS factory configuration. And on-demand benchmarks are triggered via HT Condor job submissions and are executed as a Gleiden test by modifying factory configuration, as it shows in this diagram right here. And for viewer, it's a web dashboard serving with a RESTful interface and displays the benchmark results, which also shown right here. Thank you. And so this work was done under the GeoOmni Technology Alliance program by ORISE. Thanks to Fermilab, and thank you Throughput Computing 23 for hosting such an amazing event and for facilitating my attendance. So overall summary, benchmarking is very useful in summarizing performance of a machine and to optimize resource provisioning. And it's needed to run updated benchmarks on all the resources. And GildeinBenchmark is the application that I'm developing that leverages Gleidens and HT Condor to submit customized benchmarks. And experiments can use this to rank the resources and reduce their execution costs. Thank you, everyone.